going to put up a screen for everyone. I'll explain what this is in a moment, but we're about to have a talk on Algol 60. It's the 60 years since Algol 60 existed. And I gave a talk not so long ago, which was on saving digital media and so on. And I've got my little personal collection of digital media. And you can see there, starting with paper tape, cards, then in floppy disks. You notice, although they look the same size, that's going from 8-inch down and so on. And then obviously cassettes, etc. But those very first reels you see there, that was actually my first ever attempt at programming at school. This was at Blandford Camp in Dorset, and it was writing programs in Algol 60. So those little tapes there do have some sort of Algol 60 program on them. I haven't read them for quite a long time. Sometime I want to take them along and try and get them read and see what I wrote then. But that was my starting point for programming. So I'm very interested to hear this talk. So we're very lucky to have.
For you if you want it.
Sir?
I can read paper tape for you if you want me to.
Yes, thank you. Yes, I'm planning to do that sometime. We're so busy during lockdown then. So anyway, we have two speakers for this meeting. This is our first attempt to give a talks on Zoom for the FACS, so I hope everything goes okay. We were originally going to have one speaker, Tim Denvir, who's been in the industry for a long time. I've got his CV here. It's quite long. I'm going to pick out a few points. I mean, he originally studied mathematics at Cambridge, but he's been involved with all sorts of formal methods organizations like Formal Methods Europe. He's been chair of FACS. He's been involved with the editorial board of the Formal Aspects of Computing on the FACS series of Springer, VDM standardization, etc., etc. So reading his affiliations backwards, a bit like Merlin. Most recently, he's worked for Translima, which I think is his company for doing all sorts of things, many formal methods based. But he's also been based as a professor, visiting professor at places like City University, Brunel, and so on. He's also worked at a number of companies, so working backwards, he's been at Praxis, which is one of the leading companies in the UK using formal methods, now part of Altran, so it's sort of, the name has disappeared, but it's still there. And then going back further to more historic companies, STL, going back beyond that to ICL, and then in the end of the 60s or so, about just before I was starting to write my Algol 60 programming, he was working for Radix, which I don't know, but he was working on Algol 60 compilers himself then. So his early work, he was certainly involved with compiler design at the University of London Atlas Computing Service, for instance. He worked at Elliott Brothers, and at the very beginning of his list here, he was actually at Texas Instruments doing electronic circuits. So it's quite a similar background to me, that I started off doing electronics and moved over into computing. Now, Troy is our younger speaker. So I'm going to just briefly tell you what Troy has done. He's studied computer science originally, then Troy went on to do a PhD in computer science at Newcastle University with Cliff Jones, and Troy's been interested in programming language semantics and the history of computing. So Troy's now a research assistant at Newcastle with a funded research assistant position, still working on the history of concurrency at the moment. So without further ado, I'll hand over, I think, first to Tim to start the talk off on Algol 60. So I'm going to unshare my screen, and Tim, you can share your screen.
Right, that's the title slide. So this is the Peter Landin Semantics Seminar. Apart from its being 60 years old, why should we be talking about Algol 60? Algol 60 was defined with I believe, semantics in mind. Peter Landin himself wrote a formal semantics of Algol 60 in quite early days. His formal semantics of Algol was an example of a burgeoning new interest in the formal semantics of programming languages, which took place in the 60s and 70s. So I believe it is certainly an apposite topic for the Peter Landin Semantics Seminar. I shall start off with a short history of Algol 60. I'll need to speed over that quite quickly. Then I'll do a quick run through the authors of the revised report. Then I'll talk about the relationship of Algol with formal ideas, the calculus in particular, and then give a summary of Peter Landin's approach to the formal description of Algol. After that, I'll hand over to Troy for the next few sections. And finally, if there's time, I'd like to say a word about the quote from Wittgenstein, which comes at the beginning of the description of the reference language in the revised report. So a short history of Algol 60. It all started with a conference in Zurich in 1958. That produced a preliminary report on the International Algorithmic Language, which later became known as Algol 58. It was published in the Communications of ACM. There were lots and lots of meetings going on in 1958 and 1959. An informal meeting was held in Mainz in November 58, which prompted another meeting in Copenhagen in February 59, which was called an Algol Implementation Conference, and there were about 40 people there. Incidentally, they started what they called a hardware group, which was devoted to devising the hard representation of Algol programs, concerned itself with character sets and the limitations of input equipment and that sort of thing. In 1959, the Algol Bulletin started, edited by Peter Nauer. There were 52 issues spanning 29 years altogether, starting in 59 and ending in 1988. Then there was a European Algol conference in Paris in November 59, and that sparked off an important conference in January 1960. Of those large numbers of people at the November conference, they selected 7 representatives from Europe. They were representing learned societies for computer science. In those days, the British Computer Society was regarded as a learned society. So at the same time, there was interest shown in the USA. There were two user groups in the USA called Share and Use, and each of those established working groups on Algol. And both of those organizations were represented on the ACM Committee on Programming Languages. The ACM Committee met in Washington in November 59, in parallel with all the meetings going on in Europe. They assembled all these comments that have been put forward by people studying the report. And those were published again in the ACM Communications. Amongst the USA contributors, again, 7 representatives were selected to go to the January 1960. But unfortunately, one of the reps was killed in a road accident, William Turansky. just before the January conference. Anyway, as a result of all that, a new draft report was developed from the original preliminary report in '58, and that formed the basis of the revised report at the January 1960 conference. And after January 1960, finally there was a conference in 1962 in Rome, which was correcting difficulties and eliminating ambiguities, generally clarifying. That was edited by one of the authors, the only British one, Mike Woodger. So there were, in the end, 13 authors of the revised report from 7 different countries, one each from most of the European countries, 6 from the USA. And the report was dedicated to the memory of William Turansky. I shall go fairly rapidly over the individual authors because there are 13 of them. It was 1960, remember. Computer science was not an established discipline insofar as there were no degree courses in computer science, as far as I can tell. Certainly, I was an undergraduate at Cambridge in 1960. There wasn't a degree course in computer science. There was a diploma, a postgraduate diploma of 1 year, which was organized by what they call the mathematical laboratory, which had the EDSAC computer. It's interesting to note that Peter Landin, the Danish author who edited the Algol 60 report and who edited the series of Algol bulletins, before Algol 60, he was at the Cambridge laboratory, it seemed, and he used EDSAC to calculate the orbits of comets. I thought that was quite intriguing. Friedrich Fritz Bauer, I think he must have been a man of some charisma who generated a certain slightly amused but nonetheless respect. Troy tells me that he had 2 nicknames, one amongst the Germans who called him the Pope, Der Papst, and the British people referred to him as Uncle Fritz, apparently. He was a PhD supervisor of 2 people that I'm sure quite a few of you will have known, David Grease and Manfred Roy. I didn't mean to put that in the past. Van Wijngaarden, he was for many, many years director of the Mathematisch Centrum in Amsterdam, had a background in engineering, soon moved to computing. He was involved in the first Dutch computer in 1952. Quite a lot of these authors, although they had a background in mathematics, were involved in the design of very early computers. And indeed, well, as a matter of fact, when I was an undergraduate, I did a VAC job for ICT. It was just after it had been formed from a merger between Hollerith and British Thomson Houston. Eventually got absorbed into ICEL. But if you've done mathematics and done some mathematical logic, well, here you ought to be able to do some logic design, shouldn't you? That, I think, was the thinking. So a lot of these authors, the European ones at any rate, were involved in the design of early computers. We see that they had backgrounds in maths, physics, numerical analysis, and so on. The French author Bernard Bourcois, he moved on to natural language translation, in particular from Russian into French. They went on to various other things, some of them. The last European author, Mike Woodger, the British representative amongst our list, he, when I last looked, as it were, was still alive. But if he was born in 1923, that makes him 97, so he's a venerable fellow. He was based at the National Physical Laboratory. He was involved in ACE, early computer, Algol, Ada, much active in IFIC working groups. His profile, he has a profile in Resurrection number 50. Resurrection is the newsletter of the Computer Conservation Society, and he had an early grounding in mathematical logic. I have crammed all 6 of the USA authors onto one slide here, and I've tried to arrange them in some sort of order of well, significance perhaps. John Bacchus, he's the Bacchus of Bacchus normal form or Bacchus now form, an ACM Turing Award winner. He devised Fortran, or was one of those who did so, concentrating on functional programming. He won various other awards. Alan Perlis, again, was involved with early computers and compilers. He was the very first ACM Turing Award winner. John McCarthy, mathematics again, another ACM Turing Award. He's said to have coined the term artificial intelligence. Wakestein, he had a background in physics, engineering physics, international standards. He moved on after Algol 60 to automatic fingerprint recognition. The last 2 USA authors were a bit more difficult to discover details of. Both of them were from industry, one IBM, the other GEC, but both of them were affiliated for a time with the University of Delft, I think while they were doing work on Algol 60. I was in touch with the computer science department in Delft, but they didn't find any reference to these 2. Their group on programming languages has only been in existence for a couple of years. Nonetheless, the 2 of them were clearly had involvement with Algol and had things to say about it. Here's a photo of all of them, except for John McCarthy, who was, I must presume, was taking the photo. You'll see they've all got their hands in the air, and Troy tells me that they are voting unanimously. The only time they did all vote unanimously, the question they were voting on was, are you willing to have your photograph taken? So Algol 60 and lambda calculus. I want to make this apparent by quoting 2 verbatim pieces of the Algol 60 report. The first one is about name replacement, or call by name. Any formal parameter not quoted in the value list is replaced by the corresponding actual parameter after enclosing that in parentheses wherever syntactically possible. It goes on to give an explanation of how you deal with conflicts between identifiers. So in order to obey a procedure call, you actually textually replace the formal parameter with the actual parameter, its actual text, and then deal with clashes of identifiers. Another section again about procedure calls. Finally, the procedure body modified as above, that's with the formal parameters replaced with actual parameters, is inserted in place of the procedure statement, that's the procedure call effectively, and executed. So the explanation in careful English in the Algol 60 report says you have to do this textual replacement and then execute the result. This is reminiscent of lambda calculus, the two types of conversion. The first one, where you're replacing identifiers, corresponds to alpha conversion, where if you have a lambda expression, lambda v dot e, the variable name v gets replaced by another variable v dashed, where e has every occurrence of v replaced by v dashed. And the other, the beta conversion, does the same sort of thing with the expression that follows the lambda v dot. So if you apply that lambda expression to E2, that's the result of that is to take E1 and replace all occurrences of V with the expression E2. And that is effectively what is going on with a fair amount of extra elaboration when a procedure call is executed. But it's all expressed in English in the report. The Algol Bulletin was started in 1959. As I said, it's 52 issues, and it was initiated at the Algol Implementation Conference in February '59. It was a forum for discussion of definition issues. It was eventually taken over, well, fairly soon taken over by IFIP Technical Committee 2.1, their working group on Algol. And in that later April 1962 conference, edited by Mike Woodger, which was set up to correct errors and remove ambiguities, that was reported on in Algol Bulletin number 14. And I think it was just about that time that the Algol Bulletin was taken over by the IFIP working group. The sort of discussion that went on, one colleague of mine round about the time that I was involved in an Algol compiler, they seemed to be much more concerned with properly and accurately interpreting the words of the report than the actual technological issues of the language. And one colleague of mine slightly cynically referred to writers in the bulletin as Algol lawyers. I want to just run over a few early implementations of Algol. The very first one was by Eske Dijkstra and Jaap Donneveld. It was a compiler for the Electrologica X1. And this was the very first. It was done very early in August 1960, which is impressive, I think. Having had personal experience of the difficulties in writing an Algol 60 compiler. Another fairly early one, but quite significant, was Brian Randall and Earl Russell's Whetstone compiler, so-called because that's where they were when they wrote it. It was for the KDF9, but they pretty much written the compiler before the KGF9 was ready to take it on board. So they made a reduced version for the JUICE computer. Brian Randall writes about this again in Resurrection number 50. And they did that round about 1964. Another early compiler that I had some association with was Tony Hoare's compiler for the Elliott 803. I think really it was 1962 to 63. I was working for Elliott's at the time. I, rather to my regret, wasn't in that project, but it was, so to speak, taking place in the next room. And I felt rather envious of it, but they did share their ideas with a whole lot of seminars. We gave each other seminars in those days at Elliott's, and it was a very good scheme for improving morale and making us feel that we were on the technological avant-garde. Tony Hoare reports on this in Resurrection number 48. Then there was an Algol compiler for the Atlas computer, and I think this must have been around about 1965. At least I joined the University of London Atlas Computing Service, which shared a building with the Institute of Computer Science that Jonathan mentioned. Bob Hopgood recalls that effort again in Resurrection number 50. That issue of Resurrection is pretty much devoted to Algol 50, because then it was the 50th anniversary of Algol 60. It was 10 years ago, so there was another kind of pleasant assonance for the 50th anniversary of Algol in Resurrection number 50. It was, I can assure you, used for some years, in particular by a chap who was working in my group, Chris Hodgson. He was on a contract for the Meteorological Office we understood at the time he was writing this program to simulate the Atlantic Ocean, and the Meteorological Office must have been rather pleased with it, because they kept on asking him to add more and more bits and pieces to it. So this very large Algol program grew and grew over a number of years. Now, another rather intriguing early-ish Algol compiler was in the late 1960s. It was used by Richard Dawkins. He writes about it in this book of his called An Appetite for Wonder. It's this kind of autobiography. What really intrigues me there is that Richard Dawkins seemed to be very keen on using Algol 60, which a compiler was written for it by a chap called Roger Abbott for the PDP-8. And Richard Dawkins, in Algol 60, wrote a parser generator for a syntax definition language, which was based on Chomsky's work, just the same as BNF was. The interesting thing was, the reason why Dawkins was doing this was he wanted to write the grammar of not a textual language, but a language of love songs of various different species of crickets. And by being able to define a variety of these different languages, with a bit of suitable apparatus, he could actually generate simulations of the crickets' love songs. He wanted to try this out scientifically by seeing whether or not the different kinds of crickets were attracted or otherwise by these different formats of songs. But he didn't get as far as that in his research, apparently. Wikipedia lists 20 compilers by the end of 65 and 26 by the end of 1972, but there are in fact many more because they didn't mention this one for the PDP-8, and nor did they mention one that I was involved with. But anyway, of those first 26 compilers listed, this is the distribution of amongst countries. Now, I mentioned that Dijkstra and Donneville wrote the very first one, and theirs was one of the Netherlands ones. The next four, in fact, all came from the USA. So despite one might think of Algol 60 as being kind of mostly European rather than USA, but USA were definitely very interested in it. Remember that 1960s, it was still Cold War era, long time before the dissolution of the Soviet Union and the, well, to some extent, liberalization of the Soviet bloc countries. Yet, one might think of Algol being a Western European, general Western effort, but quite a number of Soviet bloc countries wrote compilers, the USSR themselves, Estonia, Poland, and China. Comecon is the communist economic community, a sort of communist Soviet answer in advance to the European economic community. It consisted of a group of Soviet bloc countries, USSR, Poland, Czechoslovakia, Romania, Bulgaria, Hungary, I think. So I can only suppose that in listing that as a compiler, it must have been an international collaboration between some of the Comecon countries all together. Peter Landin's semantic description is what I'll go into next. His paper was in two parts, published in the Communications of the ACM in 1965, but he did the work considerably earlier than that. It was based on some lectures that he was invited to give by George Coulouris at ULIX, the University of London Institute of Computer Science, in the spring of 1963. The general series of lectures that George organized was on the logical foundations of programming. And also Peter Landin presented much the same paper, I think, titled A Formal Description of Algol 60 at an IFIT working conference in 1964. That was not so much a public paper as his CACM papers would have been. And of course, it always takes a little time, to say the least, to get papers published doing the original work. Peter Landin was not an author of the Algol 60 report, but he was an advisor at that April 62 conference in Rome, which was edited by Mike Woodger. And these are direct quotes from Peter Landin's paper. Anyone familiar with both Church's Lambda Calculi and Algol 60 will have noticed a superficial resemblance, he writes. And again, some of the semantics of Algol 60 can be formalized by establishing a correspondence between expressions of Algol 60 and expressions in a modified form of Church's lambda notation. He also writes, formal syntax has been used to practical advantage by language designers and implementers. I guess he must be referring to BNF and the like, which can be used to direct the syntax analysis phase of a compiler. And he then writes, there might be analogous advantages in formal semantics. Excuse me a second. So I think, well, I like to think that this is a seed in Peter Landin's mind that maybe having a formal semantics definition might be able to drive the other part of a compiler, a sort of foretelling of some of the work that Peter Mosses is trying to do in his semantics implementation system. One slightly irritating thing I found in Peter Landin's paper was that he makes much use of terms like acronyms and so on, which aren't defined, but only defined in the previous paper, the mechanical evaluation of expressions. So you're pretty much obliged to read that one first before you read, before you can absorb all the rest. He defines the semantics in an operational way in terms of an abstract machine that interprets a language similar to lambda notation. In general, I think Algol has an ambivalence. It tries to be simultaneously an abstraction of what an imperative computer can do. Otherwise, why would it have things like go-to statements and the horrible switch blocks, which are easy enough to implement, but hard to write a semantics for, especially in the context of recursive procedures and so on. It tries to be that, and at the same time an expression of some mathematics that can be evaluated by a computing machine. So it's, on the one hand, trying to be a decent expression of what computers do, and on the other hand, trying to formulate mathematics that a computer can carry out. His semantic description is, in his own words, over-tolerant. Again, quoting directly from his report, a mismatch will not lead to a rejection if the procedure is never applied. Now, the Algol 60 report doesn't want to let you do that if there's a fault in a type mismatch, for example, between a formal and an actual parameter that can be detected at syntax analysis time, then that program should be rejected, even though you could actually execute it. So a compiler built to that model would run programs that other correct compilers would legitimately reject. He gives initial values to declarations, which again is not really what the report requires. But perhaps we should be tolerant. I think Peter Landin's semantic description is a demonstration of what can be done semantically in defining Algol 60. It's not a definition. And that means, that domain theoretic means of dealing with undefined values wasn't to be conceived for some 8 years. Well, I think I shall finish there. And for now, I'll only have a few words to say at the end. It's time I hand it over to Troy, give you, Troy, time enough to say your part. So over to you, Troy.
Right, thank you very much, Tim. Let me set up sharing. You get a brief glimpse of my wallpaper, and then I will start my slideshow. Okay, so I'm going to talk about some work that largely comes from my my PhD research, which was into the history of formal definitions for semantics for programming languages. And in particular, I co-authored a paper with Cliff Jones called 4 Formal Descriptions of Algol 60 in their Historical Context. And particularly that will be relevant to this particular talk here. References are all given at the end of the slides, and I'm not going to hover on them, but you can get the slides later and check them out if you want to. So I'm going to give some return generally to the sort of atmosphere about programming in the 1960s, discuss 4.5 other Algol 60 descriptions, giving some brief history of each and some technical flavour. And then I'll finish by concluding, considering briefly why Algol was considered interesting in the past and why we might think so now. I'm aware this is a formal aspects group, so there's going to be some technical detail, but there are also plenty of historians in the audience, so hopefully I'll try to include some more historical stuff too. Right. So, towards the end of the 1950s and into the 1960s, programming was in something of a transition period away from the machine codes and explicit ties to particular computers and heading in the direction of more generality and more abstraction. I've highlighted IPL and Lisp particularly here, which there's an interesting point about how, as Newell, Simon and Shaw in the case of Lisp and John McCarthy in the case of IPL, or rather the other way around, I apologize for that, they were trying to find ways to express concepts from artificial intelligence, things to do with thought, which were quite different from the more standard, very numerical applications of computers up to that point. The main use of computers in the early period, the 40s and 50s, was for especially numerical analysis. It's interesting to note as a sidebar that the S expression form of Lisp, according to McCarthy, was, quote, included to impress logicians, end quote, and in fact a more Fortran-like syntax was eventually planned for the language, although the success of the S expression form meant that it didn't actually come out. Another instance of this kind of non-numerical computation is the summer school organized by Christopher Strachey in 1963, which stemmed out of an argument between him and Leslie Fox in the pages of, I think it was possibly even the Computer Journal. I don't remember which it was now. But Fox was trying to say, look, computers are tools for doing mathematical calculations. And Strachey was saying, well, you can do that, but you can also do more symbolic computation. And really, isn't that the more interesting thing? And then this summer school in 1963 was all about non-numerical computation. And one of the speakers was Peter Landin, and he talked about his lambda calculus approach. That's the title of the paper, is a lambda calculus approach. This quotation here is a quotation from Christopher Strachey, and he's talking there about his experience of working on the programming language CPL. He says, quote, this gives rise to a rather vague feeling of unease, and though we think we know what we mean about certain language constructs, we are not altogether happy that we have really got to the bottom of the concepts involved, end quote. This reflects another general trend in programming at the time, which was a desire to really understand what was going on with programming. As there were new applications and newer investigations into programming away from standard use like a glorified calculator, there was a bit of an unease about what exactly was going on. John McCarthy, to give another example, was interested in what he called mathematical theory of computation, about which I'll talk a little more on the next slide. The publication of Algol 58, or International Algebraic Language, and then International Algorithmic Language, as it was called earlier, heralded an excitement for formal descriptions. The formalized syntax that was used in those documents seemed to be a much more efficient way of representing what could be expressed in the language. And the conclusion to the initial report promises of formal semantics along the same lines. It's interesting to note the transition from algebraic to algorithmic. Does this maybe hint at the changing attitudes in programming away from something very number focused towards something a little bit more general? There's a paper by Helena Duranova and Gerard Alberts on this, the reference for which you can find at the end. And then finally, the last thing I'm going to mention is the Formal Language Description Languages Conference. This is the one at which Peter Landin presented the version of his ideas that Tim mentioned. This was held at Baden bei Wien near Vienna in 1964, September 1964. It was the first IFIP working conference, in fact, and it was intended to be a sort of a meeting of minds. It was invitation only, and language implementers and language designers were both brought along. And there was also an element of theory versus practice, as well as people who are interested in formal language description, i.e. the formal description of programming languages, and people who are interested in formal language theory. And you can see papers along both those lines in the proceedings. Okay, so this is the first description that I want to talk about. This is the sort of half description, because this is only a micro Algol. This was written by John McCarthy and presented at the FLDL conference. And McCarthy had been working on the mathematical theory of computation. In an early 1960s paper, he explicitly put this in the context of the principles of scientific advancement. He said, just like Kepler's laws of planetary motion can be derived from Newton's laws of motion, we want to know what are the basic principles of computation, and from them, what can we derive? And to him, the way that this had to be achieved was by looking at and examining programming languages and really getting to grips with what they were doing, as well as determining their correctness. So part of this was he proposed a way of writing formal syntax and formal semantics of programming languages. And you can clearly see that he'd been working on Lisp at that time. You can see the sort of the style of the presentation is very Lisp-like. There are recursive functions, and the sort of even the classic Lisp multiple parentheses show up in his approach. I'll do a little bit more about the technical details on the next slide, but basically the core idea was a state vector models the state of computation, and then statements are regarded as functions that modify that state vector. The photo here is John McCarthy, probably in the 1960s. You can just about tell perhaps that that's an IBM 7090 in the background, which gives you a hint of the date. You can also figure it out from the fact that there's still black in his hair. Okay, so a little bit of detail about McCarthy's semantics then. This is what I'm going to show for each of these descriptions. It's a very sort of top level overview, what you might call the semantic function. The micro function takes a program pi and a state, an initial starting state, or for the beginning of the program interpretation, or an intermediate one, and a statement number. Technically, it's considered part of the state, but it's treated separately. And then it gives a state. So it's a sort of, you can see here that there's an abstract conception of a machine, and it has an interpretation function. And you can see this as a clear inspiration for what later becomes operational semantics. But on the other hand, it's also presented as one big function with lambda terms in it. And you can see also there how this is an early inspiration for denotational semantics as well. Although I should say that by 1964, Christopher Strachey also had his own ideas about using functions. Nevertheless, this was the very first paper that I read when I started researching the history of programming language semantics, and I think it's an important one. It was a small and neat definition. In fact, the semantic function takes up half a page, and that's the entirety of the semantics, but it doesn't cover very much. You can do assignments, conditional statements, and jumps, and that's it. A much bigger definition is the Vienna Definition Language, VDL, operational description, published in 1968. This is the definition of Algol 60 in 1968. As a brief history, the IBM laboratory in Vienna had taken on the task of writing a formal description for PL1 in 1964. That's when they took on the task. And by, when would it be? The end of 1966, I think they published the first version of that. And it met with some criticism because it was very long and very bulky. And the leader of the laboratory, Heinz Semenek, wanted to demonstrate that this approach was just as feasible for a smaller language. Also at the same time, they had a new person joining the lab, the logician Peter Lauer, and he was asked to author the Algol 60 description, also as a method to bring him up to speed too. The core idea here is to use an abstract machine to represent the state of computation, and it's a very big state because it was originally defined for PL1. The basic idea is yeah, big state and statements altering the machine. In fact, it was so complicated, it ended up giving operational semantics a bit of a bad name. So before we look at that, let's have a quick photograph. This is probably taken around 1964. Note the Tower of Babel in the background, that's Bruegel's, it was a favour of Semantics. And some of the members of the lab here, I'll just point out some of them. Peter Lucas, who was one of the major intellectual drivers. Kurt Valk was one of the managers. That's Heinz Semantic, who ran the lab. And on the right, that's Norbert Teufelhardt, without whom Semantic could not have run the lab. He was the efficient adjutant. You can tell it's the 1960s because there's ashtrays on the table. Right, a little bit on the semantics of VDL. An interpretation function, int program, processes the overall program. It takes an abstract program, which is to say a parsed structural representation of the program, taking some obvious inspiration from McCarthy from the abstract syntax, and a state represented by xi, and returns a set of states. Now, the reason it's a set is because PL1 had parallelism called tasking, and the parallelism was represented by trees of potential executions, which were stored in the control, that's the C, and control information, CI, parts of the state. Any of the leaves of this tree would be valid successor states, and that parallelism was not really utilized in the Algol 60 definition. The other elements of the state, denotation directory, and the environment together, associated names and values. The dump was about managing contexts, and the unique name counter coped with things like own variables. You can see here some obvious Peter Landin influence if you've seen any of his papers on semantics, the stack environment control dump machine, SECD. You see this is an expanded version of that essentially. Now VDL was a very powerful definition method. It could cope with PL1, a huge language, and it could also be used to prove some different properties about languages and programs written in those languages, but it was awkward to use because of the size and complexity of it. So the next definition I'm going to talk about is another operational description written in 1972. And it stems out of the earlier Vienna work. Cliff Jones had been on assignment in Vienna in 1968, and there he'd been working on finding ways to use this formal definition to help with language design and to proving properties and so on, mainly in combination with Peter Lucas and Wolfgang Henharpel. Together with Henharpel, Jones had worked on an alternative jump handling method, which is called the exit mechanism. The idea was that, quote, jumps shouldn't take the machine by surprise, end quote, which was something that had happened in the previous VDL definition where the tree of executions was sort of slashed and totally replaced with a new one when there was a jump. This attempt to prove properties about the programs proved to be difficult, largely because the state was really big and every single interpretation function had the potential of changing everything in the state. Now, most of the time it didn't, but it had to be proved that most statements left everything else unchanged, and that turned out to be an unnecessarily difficult task. So when Jones returned back to IBM Carsley in 1970, he worked on a new kind of approach with a smaller state and this new exit mechanism. It also implemented the copy rule for procedures rather than the more complex environment and dump-based method. This Algol 60 definition was authored by Jones, Dave Allen, and Dave Chapman. The basic idea of this exit mechanism was to pass about, along with these small state components, an ABN compound, an abnormal element, which would be present if there had been a jump, and if there wasn't, then it would just be null. Okay, so the overall semantic function here, an abstract program is taken in along with a starting state, and then an end state is given. And the states here are much smaller. There's a value list VL, and a denotation and directory DN, and then this optional ABN component. It would contain a label in the case of a jump, and it would be empty if there wasn't a jump. So interpretation would go on if there was no label there, and if there was a label, then it would have to be caught using a TXI, that's exit spelled backwards, combinator. One other interesting thing about this report is that it was printed with large gaps in it. The idea was that you could then align the definition with the Algol report. I believe it was the revised report that it was based on. And then they would line up with each other. So the Algol report and the formal definition could be put next to each other. Which is a nice idea that wasn't used in any of the other descriptions. Okay, so the third and a half description that I'm talking about is the denotational semantics description written by Peter Mosses in 1974. And I must apologize to Peter, who I believe is here tonight, for the fact that I've included a photo of Christopher Strachey rather than of him, but this is because I didn't have a contemporary photo of Peter from that time, so apologies. Plus also this photo of Christopher is from the Formal Language Description Languages Conference, so it has a nice running theme. So a very rough history of denotational semantics. Strachey had become interested in programming languages whilst working as an independent computing consultant in the early 1960s. Peter Landin was his sole employee, and the two of them worked together for about 3 years, including doing some work on the autocode for the Ferranti Pegasus. During that time, Landin got interested in programming languages, and Strachey also became interested in programming languages. Side note, I didn't know about the George Caloris lectures until Tim mentioned them to me, so I'm not sure quite what place they have in this. Okay, following his consulting work, Strachey ended up working on the programming language CPL with Maurice Wilkes and some other people, including Dave Barron and Martin Richards. And during that time, this vague feeling of unease that I mentioned at the beginning of this talk began to crop up to him. Strachey decided that the best way to model computation was to use functions because they were well-known mathematical constructs with well-known properties, and handling them ought to be easier than handling the sort of abstract machines that were popular in operational semantics at the time. Strachey initially went for an untyped lambda calculus using the Y combinator for handling recursion and iteration, as Landin had used, before meeting Dana Scott, a logician, in Vienna in 1969 to meeting of IFIP Working Group 2.2. Scott and Strachey hit it off, and Scott produced his domain theory, which created a more secure foundation for the semantic style, which was first called mathematical semantics, and then also known as Scott-Strachey semantics, and later was given the name denotational semantics, as a kind of an acknowledgement that other forms of semantics could be mathematical as well. Okay, so let's talk about the Algol 60 definition. Peter Mosses was working for his DPhil on a semantics implementation system, SIS. The idea was that you could feed this system a definition, a semantic definition written in the denotational semantics style, and it would give you a compiler. In theory, that should work. Sorry, I was just slightly confused because my Siri activated. Go away. Right, I do apologize. Okay, so the semantics implementation system, in order to be fed to a compiler, had to have a formalized meta language, and this was called the Mathematical Semantics Language, MSL. And to sort of demonstrate this whole idea, this MSL idea, and also to attempt to provide a, quote, shorter and less algorithmic, end quote, definition of Algol 60 than the Alan Chapman Jones or Landin ones, Mosses embarked on writing this denotational semantics description of Algol 60. The shorter and less algorithmic quote is from that document. So a little bit on the semantic details for this. It was a little tricky to sort of pull it apart and get this out of the report. The formalized meta language is a was a little hard for me to understand. I apologize, but I think I've got the sense of it here. The compiler function is the sort of top level program, is the top level function, and all the functions here are curried. It takes a program which is a deduction tree, which sort of works a bit like an abstract syntax. It's a structural program, plus an environment, and then gives you a continuation to continuation. No, sorry, it takes a program, takes an environment, takes a continuation, and gives you a continuation. And continuations are functions from state to state, or store to store, as Strachey would have said, slightly complicated by the need to manage areas which control the blocks and procedures and sort of cope with whatever context is active at the time. It's sort of classic full-blown denotational semantics, yeah, the continuations are the main focus. Sorry, I've lost my notes. I'm just going to see if they appear if I go forward and back. Yeah, there we go. Nope, I said everything I wanted to say. Good. I'm aware of the time, so let's move on to the final one that I'm going to talk about. This is another denotational semantics description, this time back to Vienna again. And the background to this is that in the early 1970s, IBM were working on a radical new machine architecture, which they were referring to as the Future Systems Project. As part of this, they wanted to provide a compiler for PL1, and the task was given to the IBM laboratory in Vienna. They agreed to do it on the proviso that they could first write a formal definition of it, and Cliff Jones was asked to be a part of that project. He remembers that Peter Lucas called him up, and before Lucas had even finished explaining what he wanted him to do, Jones had already agreed to come along. It was an exciting opportunity. So in the time that Jones had been back in the UK, he'd heard Strachey lecture on the denotational semantics, and Hans Beckich, another one of the major intellectual drivers at the lab, had spent a year with Peter Landin at Queen Mary in the late 1960s. So between the two of them, they had heard about the denotational semantics ideas and thought this was the way to go in trying to define programming languages. They wrote a definition of PL1, first of all, the lab did, and that was published in 1974. And although it was denotational at its base, it looked more like an earlier Vienna publication with its sort of meta language being more wordy. And it used the exit mechanism and TXI combinator rather than continuations. Unfortunately, in what was known as the Valentine's Day Massacre in, I believe, 1975, February 1975, the Future Systems Project was killed, but Cliff Jones and Dinas Björner, who joined the lab around about the same time as Jones, salvaged the definition method, the Vienna definition method. This was the first use of VDM and refers to this denotational semantics of programming languages, but with a meta language called Meta4, that's meta and then a dash and then IV. It's a nice little pun that I genuinely only got when I was putting this slideshow together. Originally a language, a programming language description method, it was later adapted to specifying individual programs. As part of the salvaging of VDM and the publication in a book, there was an Algol 60 definition written as a sort of a proof of concept, authored by Cliff Jones and Wolfgang Henharpel. It appeared in the 1978 publication of the book, and then when the book was republished in 1982, it reappeared. The aim for this was an attempt to provide equal abstraction to MOSes, but more readable, according to the introduction to this particular report. Sorry, did I hear somebody saying something there? Am I being nudged for time or something? No, okay, quick chat of the chat, we're good. Let me continue rattling along. A brief description of the semantics of VDM. Again, we can see a top level meaning function looking pretty similar to the MOSes one, with the main difference being the inclusion of this abnormal part, which fulfills the same behavior that it did in the earlier 1972 definition. The trick, or a trick to this, was that the semicolon combinator was defined to be functional composition, except if an abnormal part was present, in which case then the second part of the composition would be skipped until a tipsy in the block found it, and then the label would be handled and it would all be turned into a nice jump. This also gave the trick of meaning that you could read this definition operationally, rather than composing the two functions for two sequential statements. You could read it as one followed by the other. Okay, that concludes my bit about the 4.5 definitions of Algol 60. Let's talk a little bit about some fascination with Algol. At the time, it really was, it was regarded quite highly in certain circles. There's a quotation here from Tony Hoare, which sort of encapsulates this, this almost elitist satisfaction with Algol 60, a language so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors. It became seen as something of the pinnacle of European computer science, according to David Nofra. It was seen as mathematical, precise, elegant, but inefficient. And actually, as Nofra points out, it was really an equally American project, and it was more of a sort of a stereotype than any actual grounding in fact with this idea. Nevertheless, there was certainly an Algol culture around in the 1960s, and they would refer to themselves with things like the Algol community or the Algol effort, emphasizing a sort of a shared research agenda. Algol 60 was, I'd like to think, something of a benchmark. There was certainly a time period when producing an Algol 60 compiler for your machine was a demonstration that your machine was a, you know, a bang up, proper, good machine. And that if as a research group you could provide an Algol 60 compiler, then you were doing a good job. We've already seen that there were these many definitions of Algol 60. I think it's not a stretch to say that Algol 60 is probably the most formally defined programming language of all time. And it kind of took this role because it was, well, I'll say why on the next slide, actually. I'm over-predicting myself a little bit here. Regarding influence here, I've listed a few languages which came out of the Algol effort. These first ones, Jovial and Neliac especially, were more dialects of IAL and had more popularity in America. Algol was a Germanic effort for a much more efficient Algol compiler. And then Pascal grew out of Niklaus Fiat's suggestions for a successor to Algol 60 called Algol W. CPL was influenced by Algol and went on to, through a sort of a chain of influences, become C, sort of become, and Simula also source influence from Algol. So we can see it being really an influence on a lot of important programming languages. And finally, the algorithms section in the communications of the ACM tended to use Algol for almost all of its algorithms. I believe only one algorithm in PL1 was ever submitted to the CACM algorithms. So why then? Why this fascination with Algol? Well, it had a lot of features, and indeed some of those, such as statement, declaration, type, and block, really gained their popularity thanks to Algol. The language was designed deliberately with generality in mind. It was a general purpose programming language in that you could write almost any kind of program in it, not just numerical ones. It was not aimed for a particular machine. And it was also, thanks to the work of Dijkstra and von Wijngaarden in particular, free from a certain level of arbitrary restriction. The Amsterdammers argued that if you could treat a particular variable in one way, then you ought to be able to treat the same variable of another type in the same way. And that eventually became the orthogonality principle in Algol 68. There's an article by this, on this by Alberts and Daylight. Machine independence also created an important shift in the way people thought about programming languages. Rather than earlier ones where implementations defined the language, a definition on paper makes the document the ultimate source of reference. The document therefore has to be right, And you really therefore want to properly interrogate this paper document to make sure that it's doing the right things. And when you're doing that, you can't just run something and see what happens. You have to use some more abstract techniques. So this opens the door for formalisms and reifies programming languages of objects of study in their own right. As Priestley wrote, there's a sort of a paradigm shift around the time of Algol into programming languages becoming objects of study. And on languages, there's a good paper by Priestley, Noffer and Alberts about the use of language as a metaphor to refer to computation. Dijkstra wrote in the 60s even that the formalization of the language provided an academic impetus to study programming languages, rather than just programming languages being a means to express thoughts and to write programs. They became things to look at and therefore interrogated more, and this this kind of created this sort of loop, this feedback loop of being interested in programming languages, writing formalization, and therefore being able to justify the academic focus this way. I'll just quickly mention Algol-like, and here's an appearance of Fraser Duncan, also at FLDL. He was mentioned in the chat earlier. In a comment after one of the talks, I think it was Tom Steele's talk, he mentioned that the phrase Algol-like had come to be so widely used during the conference. The only thing that everybody could agree on was that Algol itself was not an Algol-like language. What did they mean by Algol-like? That it was regular, it had blocks and procedures, it had recursion, that it was generally nice to work with, and people weren't quite so happy with Algol itself. Okay, so my final slide now. Let's talk about some of the moves away from Algol. One of the things that comes up always is the lack of industrial support. Now, there are counterexamples to that, such as Boule in France, as Mounier-Kuhn has written about, and Tim mentioned earlier some examples of compilers. But it did not have the kind of commercial support that other programming languages enjoyed. Partially, that's probably due to just industrial inertia. Another one was that it wasn't a product, and so big companies like IBM were loath to support something they didn't have control over themselves and that they couldn't sell to their customers. David Noffer makes the point that the actual research paradigm around Algol was to its detriment, because it then enforced the view of Algol as an object of research study rather than as something that was useful to customers in a real practical industrial setting. The Algol 68 fiasco I'm not going to get into, but it's worth pointing out that it scared working groups, especially Algol working groups, away from committee work for a long time and led to the demise of Algol products, and somewhat soured the end of the Algol experience. Algol, I'd like to say, is something of a turning point. I'm hesitant to say that it's like a revolution or a paradigm shift in itself, because that's not the sort of thing that gets you applause from historians, but rather part of a trend, a turning point away from languages being really tied to machines and towards programs being the object of study, with software projects getting larger and programming languages getting more complicated, a general shift away from machines through programming languages and towards individual programs and software engineering as a concept. I see Algol as kind of the turning point in the middle of that loop, sitting in the 1960s. The 1960s, a good time for formalization and for focus on programming languages, and really a kind of a birth period for computer science in the European sense. So I want to argue. I have an unpublished, submitted for publication paper on that topic, which will hopefully be coming out soon. And so to wrap this up then, here's the references to my own work on the subject. You can get copies of either the papers or technical report versions of the papers from my webpage, which is on my first slide. Here's the Algol definitions that I've mentioned, the references to them, and then some more general references, some more historical references. Right, I almost got in under 30 minutes, not quite, but I will now hand back to Tim to wrap us up. Thank you very much, and I need to stop my sharing. There we go, thank you. Over to you, Tim.
Right, I'm just trying to get this going. Come on.
It's Wittgenstein, I can see.
Is it? Yes, that's right. But I'm trying to turn it into a slideshow. That's. Oh dear. Well, maybe I'll just have to share
Yeah,
this.
we can still see it well enough.
Okay, I'll put it on. There we go. Right. The reports, the description of the reference language within the report starts with this quote from Wittgenstein. They don't attribute it to any particular work of Wittgenstein, but I've traced it to two sections of the Tractatus Logico-Philosophicus. The second clause of the quote is almost identical to the last sentence of the Tractatus, and the first clause seems to be a paraphrase of 4.116. I've translated the first clause in the spirit of C.K. Ogden, who was the official translator of the Tractatus, and I followed that with Ogden's actual translation of the last sentence. What can be said at all can be said clearly, and whereof one cannot speak, thereof one must be silent. Now the next slide. The Tractatus starts with this first couple of sentences. I have often thought that some of the best computer scientists reveal an influence from Wittgenstein, especially this Tractatus. The world, as seen by a point of control in a computer program, is the set of all variables that are in the scope of that point. And the state of that world is the value of those variables at that dynamic point. One might say that a principle of programs as predicates equates a state of the program's world with a set of all true propositions about it. That is the facts, or everything that is the case. I wonder if it would be whimsical to conclude that the authors of the Algol 60 report were presaging the concept of programs as predicates. Troy mentioned the kind of spirit of the time of semantics of programming languages, and there was a parallel spirit of the time in philosophy, which started to focus on linguistic philosophy, which, to put it as a caricature, might be saying that things don't exist. All that does exist are the statements that we can make about things. And I can see a sort of going hand in hand between that movement in philosophy and the movement towards semantics in computer science. That's all I have to say. This is a list of my references. I would like to make two acknowledgements. One is to Case Pronk, and I noticed that I think he's in our audience. He sent me a number of private communications, which helped me chase up some details of the authors. He sent me a list of the USA computer scientists who have the surname of Katz, and I emailed all of them, there were about 8 or 10 or so, to ask them if they were any relation to Charlie Katz, who was one of the authors from the USA of the revised report. To my amazement, they all replied within a day or two, every single one of them, very politely saying, no, sorry, very interesting, but I'm no relation to Charlie Katz. I'd also like to recommend this book by Mike Gordon. His chapter 4 has a wonderful introduction to the influence of lambda calculus on computer science. And then if anyone wants to learn about the lambda calculus, the rest of his chapter is a very good tutorial. So that's all. Thank you, Troy, very much indeed for your contribution. And over to you, Jonathan, back as chairman.
Right, well, thank you very much to both of you, Tim and Troy. I'll give you a little. It's difficult. Anyone else who wants to clap and unmute briefly? Well, one thing I'll say is if John is there, John Cooke, I lost contact and I'm no longer a host. Only you have the power to make anyone a host now. So if you can do that, if you're there, John, I can't see you or hear you, but at least I can talk to everyone and hopefully I can organise questions. So if anyone wants to ask a question, we can stay on for a while. Thank you, John. If you can make me host, where you have to point to me and select me to be a host.
Okay.
So,
if you're able, but anyway, are there any questions? If you want to,
yes,
we can try by just unmuting.
I have one.
Okay.
I'm Simone Martini from Bologna, Italy, and I have a question for Tim. Now, you mentioned several times the relations between the Algol report, the procedures definition, and the passing by name and lambda calculus. Do we have any evidence that this relation was clear to the Algol committee at the time it was defined the language, or it is a creation of Peter's?
I don't have any evidence that it was in the minds of the writers of the Algol 60 report at the time, but it's something that I noticed, and then I discovered that Peter Landin had noticed the same thing when I read his paper. That's all I can say, really. No, there's nothing in the report or anything else that authors have written to indicate precisely that they had that lambda calculus in mind.
Yeah, thank you.
I have read something somewhere about there being a bit at one of the meetings there was a discussion of, well, this is basically the same as lambda calculus, so why don't we just explicitly say that it is? Unfortunately, I remember that. I don't have a citation for it. I don't remember where I saw it, but I do believe that was mentioned at some point. Ah, no, here we go. It's all right, I found it. In Peter Landin's FLDL talk, the one given in 1964, Fritz Bauer commented and said that during the, quote, chaos, end quote, of trying to fix the semantics of procedures, there was a group advocating the use of lambda calculus in this context, but it didn't end up happening. So yes, there is some evidence that they were aware of lambda calculus.
Great, thanks.
I'll just ask again, John, if you could look at the chat and make me into a host. At the moment, we're losing the recording of this bit. Thank you. Troy may have a recording, hopefully. Anyway, if anyone else has got a question while John tries to do that, just unmute and ask.
Just a comment, really. Well, after Tim had written his article, FACS, I looked into Algol because I'd been on a short course in the 60s. And as a result of this, I found a document which I can't find now. Whole load of algorithms are creating mathematical physics functions using Algol. And I wondered if that was who it was. It sort of disappeared into the abyss of mathematical physicists. You know, after it was first produced. You know, you said it wasn't picked up, but I wonder if that's who it was. If I find it, I'll send it to Tim, but I can't find it at the moment. Okay, that's it.
Thanks, Margaret. Any other comments?
I have a comment.
Go ahead.
Yes, I might add a comment. One thing that Troy forgot to mention, I think, is the wonderful library of semantic descriptions that Cliff Jones has assembled on his web pages. These were digitized, and they have not only the visual presentation of the original documents, but also a PDF layer underneath with the source text, so you can actually search in these documents. That includes my Algol 60 description and Cliff Jones's own Algol descriptions. I don't know if Cliff is online. He'd like to say a bit more about it.
Well, I can see Cliff there. So
I'd have nothing to add. Thank you very much, Peter, for pointing it out. I'd forgotten.
Yeah, thank you. I'll find it and I'll put it in the chat.
any other questions?
I have a question.
Go ahead.
One of the speakers mentioned, I think, a paper by maybe a Priestley or a Duncan called On Language, and I missed that reference and was curious what it was.
The entrance of the language metaphor to describe programming.
Yes, I think that's it. Yes.
Yeah, okay, I'll get that too. It is in my slides, but I can put the reference in the chat easily enough.
Great, thank you.
I have a comment and a question. It's, I mean, clearly, if you look at Algol, some aspects are clearly reminiscent of lambda calculus. I mean, in particular, call by name, and you know, also Jensen's device, which is essentially just a lambda. But at the time, call by name is not very easy to implement. It's fairly inefficient and got replaced in later languages by call by reference. Now, there are some suggestions that it was call by name was a mistake, and that they really meant call by reference. They just didn't describe it properly, or some reason. On the other hand, it really just mirrors normal order evaluation in lambda calculus. Does anybody know where have any views or information on this?
Well, in Algol 68, they moved on to call by reference. So that is some sort of evidence that maybe they did intend that call by reference in the first place. But incidentally, in about, yes, very early 1970s, ICL were producing a new range of computers. I've forgotten what they eventually called it, but nearly all the systems programming that they did for that was in a private language to ICL called S3, which was a subset of Algol 68, and that used call by reference as a way of parameter passing. So in Algol 68 did have some industrial use in a subset afterwards. Not for very long, I don't think.
Yes. My question was really, did they change because of the implementation and difficulties and inefficiencies? And was it originally they really were trying to mirror lambda calculus, which is what you would think, because the description is just like normal order evaluation?
I'd rather think it was a combination of the two. They liked the idea of mirroring lambda calculus, but later on probably realized it was more practical to use call by reference.
I also think that there's an argument that it might not have been really understood at the time, that these ideas, so McCarthy, for example, famously got the lambda bindings wrong in the early versions of Lisp. I don't personally have enough familiarity with lambda calculus to remember off the top of my head exactly what it was, but I know that there were arguments about whether call by name or call by value was sort of better There's a letter written by McCarthy in 1965 where he calls Algol 60, quote, mathematically ugly. The call by name concept uses irrelevant properties of the names of variables because there's no good way of binding the variables, end quote. There's a nice little story about an argument between Peter Landin and John Reynolds about the nature of the denotational semantics meta language, which I will find and I will describe, but I have to find it.
Any other questions?
I have a comment on both speakers refer to what was in the air at the time in the early 1960s or late 1950s, and I would like to the comments of both speakers on the use of the word semantics. Modern language theory was very much in the air. Chomsky was published and well famous in the 1950s, but just like ideas of the ideas of recursion and Lambda calculus, it was there, it was around, and in writing the Algol report 1960, they used the word semantics, but in a very vague, colloquial way. And when 4 years later, Peter Landin comes on and formalizes that, that is a whole new development in itself. And so to me, there's a strong distinction between the everyday use of the word semantics, which was a very, was really a buzzword of the day, but nobody actually knew very much what it meant. And then Peter Landin and later Dana Scott coming in and giving a really formal definition of semantics and taking syntax and semantics as a formalized relation rather than an everyday use term.
Well, I'll make an initial comment on that. I think you're quite right that there's a shift in this idea of what does it mean to talk about semantics. And regarding Chomsky, he was one of the people invited to go to the Formal Language Description Languages conference, but he turned down the invitation. But it shows how clearly linguists and the ideas of people working with formal language theory were regarded in this kind of community. So that was in 1963, they were putting together the invitation list. And there's also, there's another earlier conference called Working Conference on Mechanical Language Structures, which was held in Princeton in spring 1963, I think. And this was supposed to be, it was intended to be a mostly kind of syntax focused kind of affair. But the summary remarks about this, which were written by Saul Gorn, show that actually everybody was talking about semantics. And this is some of the earliest published remarks of people like John McCarthy. So I think John McCarthy there says something like, what we mean by semantics is a function which describes the transition from state to state. And Saul Gorn, in fact, argues against that, saying semantics is in the head. Semantics is what I have in my mind when I'm thinking about how something operates. And as soon as I write it down, it's something else. It's not semantics anymore. So I think that's the kind of the transitional period, is that sort of 1960 to 1964 kind of period. Tim, you have something to say on that?
So I think it's, no, I don't think I've got anything to add, really. You know, it's rather difficult to tell after the event, but I think Troy has expressed it very well.
Can I tell this this anecdote now about John Reynolds then, perhaps? It
sounds good.
Originally, it comes from Olivier Denvir, and he explains that he was having lunch in France in 1997 with Peter Landin and John Reynolds. And he says, quote, "I took the opportunity of a pause in the conversation to venture the question as to whether in their mind, the evaluation order of the meta-language of denotational semantics was call by value or call by name. Peter and John immediately and simultaneously answered, call by value, of course, for Peter, and call by name, of course, for John. For a second of eternity, they looked at each other. Then it was like they were mentally telling each other, let's not have this discussion again, and the universe resumed its course." End quote.
Very good. Any more questions? We can continue a little bit, although we'll run out of time at some point.
Will this video be available, or is there a video? Is it a recording?
I hope so. I dropped out, but I think it's going onto the cloud, and Troy has a copy as well. So one way or another,
Yes.
we'll get it onto YouTube.
And the slides as well.
Yes, we can link the slides on the BCS FACS website from the page for this talk. So we'll do that as well, provided the speakers agree, of course.
Well, yes.
Yeah, good. Are you happy with your notes to go on, Troy, or do you prefer just the slides?
No, the notes is fine as well.
Okay. Well, maybe that's a good point to say thank you very much to our speakers. It's been a great tour de force through early Algol 60. I was wondering when Algol 68 might get mentioned, because I did use that as well very briefly with the 7-pass compiler at Imperial College. I loved the 7-pass compiler because as it ran, each time it would find an error, correct it, and then the next pass would say, no, that was wrong. This is actually what you meant. And each pass would go on. So you can see why it was a fiasco, I think, from my experience of Algol 68. But anyway, thank you for a very nice talk that was certainly not a fiasco to Tim and Troy. We can clap if we can. But
Thank you. Thank you very much.
It doesn't work that well on Zoom, but anyway, thank you very much. I very much enjoyed it, and I hope everyone else has. It was wonderful to see Peter Mosses and other people here as well involved with the story, and Cliff.
It's great, absolutely great.
And we hope to have a write-up by John Tucker as well on the talk, which should appear in the FACS newsletter early in the new year. So I guess it just remains for me to say happy Christmas to everybody. Hope you have a good break, whatever you're doing. Stay safe, of course. And I think we're going to have some more Zoom talks in the new year. We haven't quite decided what. If anyone wants to volunteer for a Zoom talk, please get in touch with me. And then we'll go back to real talks, probably with Zoom as well in parallel when that's possible. But for the moment, the BCS have made no announcement on when the offices will be open again. So I think we're stuck with Zoom for the moment. Anyway, it does make recordings and so on easier, and we can have people from all over the world visiting. We've certainly got at least one person from the US, and maybe a few other people who couldn't have come otherwise. So,
exactly.
Thank you very much, and bye. See you in the new year. Happy Christmas.
Everybody. Happy Christmas, Happy New Year.